So let me go ahead and share my screen here. Okay, there we go. So with section 4.3, let's start with, okay, number 20 over here. And this is just talking about plotting the complex number and finding its absolute value. So that's number 20 over here. Okay, so if you're talking about plotting these, then of course we have the horizontal axis. Remember, that's the real axis.
Mhm.
The vertical is imaginary. So can you tell me how to plot this point?
So we're just gonna write it out as like -8, 3.
Very good, yeah.
And those would be our plotted points, and then we just graph it. So the imaginary would be 3, and then over -8.
Yeah, so negative on the real axis and then positive on the imaginary axis. And then when we are talking about the absolute value, we are of course talking about that distance from the origin. So how will we go about finding the absolute value for this?
Square root of a squared plus b squared.
Very good, yeah. So that would be absolute value of a complex number. And what will that end up giving us?
64. Square root of 73.
Root of 73, okay, so you will get 64 plus 9. All righty. Very good, yeah, nicely done. So you guys are okay on this?
Yeah.
Okay, very good. Let's see, the next one I have for us is number 24. And the instructions are find the sum of the complex numbers in the complex plane. So that's number 24 over here. Okay, so what will we need to do when we're talking about adding these in the complex plane?
We're first gonna combine like terms, so it'd be like 2, and then like, yeah, so it'd just be 2 plus I.
Okay, yeah, so you're taking the real parts together and you are taking the imaginary parts together. So that's -1 plus 2. So 2 plus I. Now, if you had to draw these as vectors, what would we go ahead and do?
If we had to draw them as vectors, so it's just kind of like, so we draw from the origin, so we do like 3 -I, so that'd be just 3 and -1.
Very good.
And then -1 plus 2I would just be -1 and 2.
Yes, if this is the first vector.
Yeah.
And then this guy is -1 and 2. So that means you are going where to draw this?
From the point of vector u, like the tip of it.
Yeah, so this would typically be if we were drawing this from the origin, but if we're drawing this from the tip of, let's say, vector u, then how would you draw that?
You'd move it up to, you'd move it to the
So from
right
this tip, we would
2.
need to go left 1
Yeah.
and up 2, right? So we would go left 1 and up 2, which would place it right over here. Something like this. And then of course you are talking about this distance here as the sum. And does that verify with our 2 plus I?
Yes.
Yeah, because this value here is lining up with positive 2 and positive 1. Yeah, very good. So that's exactly what we need to do. And of course, we don't really need this guy. Okay, so yeah, you can verify this by just using the sum of complex numbers like we saw in 4.1, but then just make sure you're comfortable working with the vectors also. So this guy was number 24. Now let's look at what's our next one. Okay, so this one is talking about finding the difference in the complex plane, and we are looking at number 30. Okay, so what happens with this guy?
It just reflects over the real plane.
Okay, so let's go ahead and do your regular subtraction, and what will that end up giving us?
-6. Yeah, -6 and 2.
Shouldn't it be
No, it'd be no I. Yeah, no I.
0, right?
0, yeah.
Yeah, because you've got a coefficient of positive 1 on that first one, and then that minus sign, and the coefficient of positive 1 on the other one. So you get -6 here, and you get 0i, which means we're just getting -6. So again, if we try to do this with vectors, so for that first complex number, what will our vector look like?
To the left of 3 plus 1.
Yeah.
Or up 1.
So yeah, go left 3, +1. So this will be our vector u. And then what's the value for vector v?
It would be to the left 3 and up 1 again. Or down 1, sorry.
Hold on a second, let's see. Okay, so the vector itself is +3 and +1, right?
Yeah.
But when we are, since we are doing a difference here, a subtraction, we basically want to take the negative of this vector. So that means you are actually looking at -3 and -1, which means from the tip of the u vector that we just drew, we would be going to the right 3 and down 1, because you're basically going in the opposite direction, right?
Okay. Yeah.
So that, sorry, not to the right, to the left, because the original was positive 3. So you're going to the left 3 units and then down 1. So And my
So we
pen
believe this
obviously
factor.
just stopped working at this crucial time. So I'm going to draw this by hand,
Oh boy.
what this will look like. But hopefully you get an idea. So this is what we would have to be doing. Going left 3 and then down 1. So you should basically come back to the original real axis, right?
Mm-hmm.
And then of course you're talking about this vector here as our difference. So that should of course verify and go all the way to -6 on that negative side. Okay. Adrian Medina, I think, just came in. Adrian, how are you doing? Did you have any questions about this?
I'm doing okay. I just came to see some examples, like some walkthroughs.
Okay.
Problems.
All right, guys. So that was number 30. Now, let's look at how to complex number and its complex conjugate. And then, of course, go back and rewrite the conjugate as a complex number. So we are looking at number 40 over here. The first thing we need to do is go ahead and plot this. So what will be our ordered pair for this complex number that's given to us?
-7 and 3.
Alrighty, -7 and 3. So that means you're going on the negative real axis, 7 units out. And then going up 3 on the positive imaginary axis, right? Okay, so if this is where, come on. Okay, so where are we going to draw the conjugate for this?
At -7 and -3, because it just reflects over the real axis.
Very good. It reflects over the real axis, so we would just be going down to -7, -3. And what will that look like in terms of a complex number?
Would it be -7 minus 3i?
-7 minus 3i. Yeah, very good. And if you remember from section 4.1, we had basically talked about how for a plus bi, its complex conjugate is going to be a minus bi. So that's basically what happens is that plus 3i from the original number will end up becoming minus 3i in the complex conjugate. So that's going to be your answer. Okay. Okay, how about, what are they asking us to do here? Oh, finding the distance between the complex numbers in the complex plane. So we're looking at number 44 over here.
4, -7.
So what's our distance formula here?
Distance formula for the complex plane is the square root of s minus a in parentheses squared plus t minus b squared.
Yeah, very good. So basically you take the difference between the real number parts and take the difference between the imaginary parts. So yeah, s minus a squared plus t minus b squared inside our square root. And in this case, you can think of these numbers here being a plus bi, and you can think of this as being s plus ti. So when we plug this in, s would be positive 3. Now what is a?
A is -7.
-7. So just make sure you have two negative signs in this first part, plus t is 5 minus, and you'll notice b is also -3, right?
Yeah.
So again, we should have two negative signs in our second part here. So of course, two negatives means they will become positive, which means you will end up adding these numbers inside the parentheses. So 7 plus 3, of course, will give us 10, and that's going to be 10 squared. 5 plus 3 will become 8, so that becomes 8 squared. And as a radical, what are you looking at as the distance?
Is that the square root of 164, which is 2 root 41?
Yeah, very good, because 10 squared becomes 100. 8 squared is a 64, so that will end up giving you 164 inside the radical. And then just to find its decimal approximation, sorry, you gave me a simplified answer, didn't you?
Yeah, I gave you a simplified answer,
So what did
not
you
the decimal approximation. Let me find that out real fast. The decimal approximation is 12.81.
Okay, and what was your simplified answer?
It was, sorry, let me go back to it. 2 root 41.
Okay. Yeah, so basically you can break down that 164 into 4 times 41, and the 4 comes outside as 2. So just look for your instructions and see if they want a simplified radical or do they want a decimal approximation. And I think in the examples they had done rounding to 2 decimal places, but you can again kind of see what your homework problems ask you to do. Alrighty, very good. So did anyone have questions on this one?
Nope.
You guys okay?
Yeah.
Alrighty. So our next example, we actually want to look at our midpoint, how to find the midpoint for two complex numbers. So let's look at this one over here. So it says find the midpoint of the line segment joining the points corresponding to the complex numbers in the complex plane. And we are looking at number 46 over here. So what are we looking at as our midpoint formula again?
Midpoint formula is a plus s over 2. And then the second point is b plus t over 2.
Okay, very good. So again, add the two real parts together, divide by 2. Add the two imaginary parts together and divide by 2. So if we graph these, we would have -3, +4. Basically, if these were our line segments and the ends were our two complex numbers, you're basically trying to find what the midpoint for this line would be. Okay, so what values are you adding for the a plus s?
-3 and 1.
Very good. And for b and t?
4 and -2. So then it'd just be 4i minus 2i.
Oh, you don't need to worry about the I.
Okay.
So what do we end up getting then?
I got -1 and 1.
Okay. All right, yeah, because this will give you -2/2, which will end up becoming -1, okay? And this one will give you +2/2. That becomes +1. So we are looking at -1, +1, which would be right over here. Okay, very good. So you can really see that, you know, all of these examples are very basic. They just want us to be comfortable working with complex numbers. And of course, in this case, they are doing it more geometrically in terms of the complex plane. So any questions on any of these examples here?
Nope.
Alrighty. So let's see, our last section for chapter 4 is going to be 4.4.
The trigonometric form of a complex number.
There we go. So let's see, for 4.4, let's start with number 10. So your instructions are plot the complex number, then write the trigonometric form of the complex number. So again, we're looking at number 10 over here. So if we had to, that's not how I want to write it. Put I in the middle. Okay, so if you wanted to graph this, where do we place it? Because approximately what is 4 square root of 3?
Square root of 4. Let me find it. 4 square root of 3. 6.93.
Okay, so approximately 7, right?
Yeah.
Okay, so we will need, what will be our ordered pair over here?
Would it be 4 comma up the 6.92 or about 7?
Yeah, just approximately. Of course, when you just look at it in terms of the numbers given, your ordered pair would be +4 and then -4 square root of 3. But we know this guy is approximately going to be close to -7. So what quadrant does this fall into?
Quadrant 2? No, wait. Quadrant 4, sorry.
Quadrant 4, yeah, because you have the positive real and the negative imaginary. So you're kind of looking at +4, -7. So maybe somewhere over here. And of course, this will be our 4 and negative 4 square root of 3. So that's the plotting part. Now they are asking us to rewrite this in the trigonometric form. So what do we do first?
We do the square root of the 4 squared plus the negative 4 root 3 squared.
Yeah, because remember in trigonometric form, our number is defined as, oops, r times cosine theta plus I sine theta, right? Which means we need to find what the value of r is, and then we need to find what theta is going to be. So your r is, of course, the absolute value of the number. So it's defined as what we saw in 4.3. So that's a square plus b square. So our a square in this term is, of course, 4 square, plus our b square was negative 4 square root of 3 squared. So simplifying that, what will we end up getting?
16 and negative 12, or is it negative 12, or would it just be regular 12?
No, because you're doing negative times negative. So it will end up becoming positive. So yeah, 4 squared will give you 16. And then on this side, the negative times negative becomes positive. 4 times 4 will be 16. And what happens with square root of 3 to the second power?
It becomes 3.
It will become 3. Yeah, so this one we have to be careful about. And then what is 16 times 3?
16 times 3 is 48.
48. So we are adding 16 plus 48, and that will give us
64
okay, and square root of 64
is 8.
Okay, there you go. So we have our R value. So that takes care of that first part. Now we need to find theta. So since this is a quadrant 4, so since our Z lies in quadrant 4, remember to find theta, we have to use
I plus arc.
2 pi plus, oh, come on, arc tangent of B over A. So the first thing we're going to do is start by finding our tangent. Okay, this guy really does not want to work today. Here we go. Tangent of theta is B over A. So our B, of course, is negative 4 square root of 3. A value is 4. So the positive 4 and the 4 from the numerator will cancel each other out, leaving us behind with negative square root of 3. Now, where is tangent value going to be negative square root of 3 at?
Is it at pi thirds?
Yeah, so at pi thirds, which is the 60-degree angle, you will have positive square root of 3 over 2. So for its negative, you can just think of your theta being as negative pi thirds, right? If you go in the clockwise direction. So you can say theta can be negative pi over 3. So when you put it in here, for arc tangent of b over a, what would that be? What would you plug in there?
Arctangent.
Because here you're talking about arc tangent of negative square root of 3, right? Because b over a simplified into negative square root of 3. So for this value here, what do I put in? Do I put the
Just negative pi thirds?
Yeah, you put the negative pi over 3, add that with 2 pi, and what do you end up getting? So that will become 6 pi over 3, and then you've got negative
5 pi thirds.
Yeah, very good. 5 pi thirds is going to be our theta. So now that we have both the r value and the theta value, you just have to put it in this format over here now for z in the trigonometric form of the complex number. So our 8 equals r, and then we've got our theta over here. So that will now become 8 for the r value, cosine of 5 pi over 3 plus I sine of 5 pi over 3. Those are the two crucial things you have to find to convert from any standard form of the complex number into the trigonometric form. Question on this one, guys?
Nope.
Everybody's okay?
Yeah.
Okay. 10. Now let's look at this one here. And so here, they're actually giving you the complex number in the trigonometric form, and they're asking us to rewrite this in the standard form, and then of course plot the complex number. So you are looking at number 28 over here.
5 cosine 135 plus unit circle.
So what's the first thing we should do?
Convert the cosine of 120 into radians. Would that be the first thing? Or graphing it?
No, you don't really need to. If you look at the unit circle, what do you see?
We don't have our unit circles in front of us.
You don't?
I just pulled up an image for it.
Okay, there you go.
135 is negative root 2 and 2, 3/4. Cool.
Yeah, so exactly. You, as long as those are the angles from your unit circle, just use your unit circle. And if there are angles that fall outside of the unit circle angles, then you would have to use your calculator, okay?
Cool.
So cosine gives you negative,
Or cosine gives you, I think, positive root 2 over 2, and sine is negative root 2 over 2.
okay? So look at this unit circle again. So cosine is the first coordinate or the second coordinate?
The second coordinate.
No, cosine is the first coordinate.
Ah, damn.
Because remember, it goes in alphabetical order. So cosine will be first and sine will be second.
That's a bad one.
So cosine will be negative square root of 2 over 2. And sine will be the positive square root of 2 over 2. And then we still have that 5 on the outside. So what do we do now?
We just distribute the 5.
Yeah, very good. So distribute that 5 with both values. And we will basically end up getting negative 5 square root of 2 over 2 plus I 5 times square root of 2 over 2. Now, if the 2 in the denominator could have canceled out with the 5, then of course we would have tried to simplify that. But since that does not happen, you can leave it just the way it is. And just normally in writing these numbers, we prefer to put the I in the back instead of the front. So this is how you are converting this from trigonometric form into the standard form. So like I said, remember, if these are angles that you can find on your unit circle, then just use those values. But anything outside of that, just use your calculator. And then depending on if it's in the radian mode or degree mode, just make sure your calculator is in that mode, okay? So any questions on this one, guys?
Nope.
Okay, so let's look at our next example here. Okay, so same thing. This time you are given, and we're looking at number 34. So again, converting it from the trigonometric form to the standard form.
Where do you...
Oh, we didn't graph it in that previous example. If you had to graph this, where would you place it?
It would be in the second quadrant, and the decimal approximation for it is 3.53, so about 3.5.
Okay, so yeah, quadrant 2 is right because we have negative for the real value and positive for the imaginary value. So approximately 3.5, right?
Yeah.
So that would be 3.5, maybe. Oh, I don't know, somewhere over here, if this will let me graph it. Come on, buddy. There we go. And then, of course, just its distance. So this would be your negative 5 square root of 2 over 2 and positive 5 square root of 2 over 2. Alrighty. Okay, so what's happening with this one here? And again, if you need your unit circle, you can take a look at that. So what do you think this guy will become in standard form?
What were the points again for it?
8 cosine of pi halves plus I sine of pi halves.
Cool.
So what is cosine of pi halves?
Cosine of pi halves. So, 0.
Okay, and sine of pi halves.
1.
Alrighty. So this will basically end up giving us 8 times, what will that be? Just 8 times 1i or just I?
Yeah.
Which will become 8i. Now, if you had to plot this, where would we put it at? So how would you graph this guy?
On the imaginary plane, you would just go down 8.
Go down?
So it'd be, yeah, or up, sorry, not down. So it'd be 0,8.
Yeah, because your real part is not here. So that tells us that the real part is going to be 0, and then the imaginary part is 8, which means you are looking at positive imaginary axis, right? And you're going
Yeah.
up to 8. So that's where you would place it. And then this would just be your distance from the origin. So 0, 8. All right, very good. Okay, so this was just to show you the difference between when you have your angles given in radians, and of course here, our angle was given in degrees. So that was only the difference between these two examples. So let's look at right here. So they're saying find the product, leave the result in trigonometric form. So we are looking at number 44 over here. So the first complex number is 1/2 cosine of 100 degrees plus I sine of 100 degrees, and we're multiplying this by 4/5 cosine of 300 degrees plus I sine of 300 degrees. So do you remember the rule for when you are multiplying two complex numbers?
I don't.
Okay, that's all right. You will find it in 4.4. Okay, so right here. Now, obviously, you can always do the FOIL method like we had seen in 4.1, but since we are talking about two different degrees in our cosine and sine functions, this first one where you're saying Z1 times Z2 is where we take the modulus for each of our complex numbers. So R1 gets multiplied by R2, and then in the parentheses, you will have cosine, and then we add the angles, theta 1 plus theta 2, plus I sine, again, theta 1 plus theta 2. So basically, when you're multiplying, multiply the moduli. So R1 times R2, and then basically with the cosine and sine functions, you go ahead and add your angles, the theta. When you are dividing them, it's going to be R1 divided by R2. And then, of course, you will see with the angles, we are subtracting the first angle minus the second one. So we'll be looking at examples for both of these. So let's go ahead and take a look at this one here. So again, you are taking the 1/2, multiplying it with the 4/5. That's your R1 times R2. So that will be in the front. And then on the inside, we are going to be taking cosine and then adding our angles together. So that's going to be 100 degrees added with 300 degrees plus I sine, same thing, 100 degrees plus 300 degrees. So when you multiply 1/2 with 4/5, what does that simplify into?
Does that come out to 1/10?
Say that one more time.
1/10?
1/10? Nope.
Yeah. Oh my gosh. 2/5, sorry.
Yeah, very good. Because the 2 here can go into the 4 2 times, so it will end up becoming 2/5. And then what happens here with our angles?
It becomes cosine of 400.
Okay, and then since we know 400 is obviously larger than 360 degrees, we can use the idea of coterminal angles. So 400 is equivalent to which angle between 0 and 2 pi or 0 and 360?
400 cosine 360.
And I don't know if looking at a unit circle will help you. So what do we normally do with coterminal angles?
Subtract or add 2 pi.
Okay, and so since we're doing this in degrees, what would you do with this?
It's equivalent to, isn't it 40 degrees that it's equivalent to?
Yeah, very good, because all you have to do is just go ahead and subtract 360 degrees from this, and you will get your coterminal angle, which of course comes out to be 40 degrees. So this will break down to cosine of 40 degrees plus I sine of 40 degrees. Now, since they are specifically asking us to leave this in the trigonometric form, we don't have to do decimal approximations for cosine of 40 and sine of 40, okay? So this one specifically, we will just drop right here. Okay, did any of you have any question on this? Okay, so let's see. For the next one, our instructions are find the quotient, and again, leave the result in trigonometric form. So for the quotient problem, let's look at number 50 over here. Okay, are you guys done writing the problem down?
Yeah.
Here's your rule for the quotient.
For the quotient. Theta minus 1, theta minus 2, C2 cannot equal 0. So that's just 4 or 5.
So this is where we subtract our angles, right?
Yeah.
Now, of course, we cannot reduce down 5 over 4, so we will leave it as it is. And then what does your angle become after you finish the subtraction?
4.3 minus 2.1. 2.2.
Yeah, very good. 2.2. And are these angles, oops, are these angles in degrees or radians?
Radians.
Very good. Yeah, because you're not seeing the degree symbol on these, so we know these angles are radians. And again, they're asking us to leave it in the trigonometric form, so this is where we stop. Okay, so any questions on the product rule or quotient rule? Alrighty. So we've got just one more example here, and this one is find the product in the complex plane. So this is where we need to do this. You can do it simply just the way we did our product rule right now, but I also want to see the vector geometric representation of this also. So we are looking at number 62 for this guy.
Pi fourths. 2, 2.
Okay, so remember in vector form, we'll take the first complex number, and that would be 2 on the outside for that r value. And then these would be cosine of pi over 4 and sine of pi over 4. In that same way, we can write vector u, which would be 3 on the outside, and cosine of pi over 4 sine of pi over 4. So what is cosine and sine of pi over 4?
Root 2 over 2.
Yeah, and it's going to be the same for both cosine and sine. So these guys will then become, again, that 2 on the outside, square root of 2 over 2, square root of 2 over 2. And this guy will have a 3 on the outside, square root of 2 over 2. So cleaning these up, what will we end up getting?
For the left-hand side, it's just going to be root 2, root 2.
Yeah, because each of these 2's, of course, you will distribute that 2 on the inside, and then your 2's on the denominator end up canceling it out. So you just basically get left behind with those numerators. And then what happens on this side?
It becomes 3 root 2 over 2.
Yeah, because nothing cancels out here, right?
Yeah.
So that 3 will just get added on basically on that numerator, or technically gets multiplied. Okay, now if we had to graph these guys, where would we graph them?
At the decimal approximation for root 2, 2.
Yeah, so square root of 2 is approximately 1.4. That would be, which quadrant would vector 2 fall into?
The first one.
First one, yeah, and you're looking at about 1.4 and 1.4. So something like this, and that will be our vector 2. Now, where will vector v fall into?
The first quadrant as well.
First quadrant as well. And what kind of decimal approximation?
It's got 2.12.
Okay, so 2.12, so just a hair above 2 and 2, right?
Yeah.
Well, maybe, I don't know, somewhere over here. Okay, so that's going to be our vector v. Now, when we are talking about the product, we will need to do the magnitude for each one of these vectors. So remember, magnitude calculation is basically your absolute value calculation. So the magnitude for vector u is basically going to be square root of 2 squared plus square root of 2 squared, right? You take each of these coordinates and you're going to square them and put it inside a square root. And so what will this come out to be?
Would it come out to be 2?
Right?
Because square root of 2 squared is just 2, so 2 plus 2 is 4.
Right, because your square and square root just end up canceling each other out. So like you said, square root of 2 plus 2, which is of course square root of 4. And oops. Square root of 4 will of course come out to be 2. Now what will be the magnitude for vector v? So these guys were 3 times square root of 2 over 2. Square that. Same thing for the other guy.
It comes out to be 4.5 for 3 root 2 over 2 squared.
Okay, yeah, so you will end up basically getting, okay, let's do this over here. So 3 squared will become 9. Square root of 2 squared will just basically end up becoming 2. And then on the denominator, the 2, again, you square that. So 2 squared will become 4. So what will happen, this 2 will cancel out with that 4 in the denominator. And you will end up getting 9 halves when you clean these guys up. So you're basically looking at, like you said, 4.5 or 9 halves. And when we add them together, what do we get?
You get 9.
Yeah,
No,
very
wait.
good.
Yeah, 9.
Yeah, because you're doing 4 halves plus 4 halves, which adds up to 9. Or if you do it with fractions like I did here, since they have the same denominator, you basically have 18 divided by 2, which will also clean up into a 9, right? So
Yep.
square root of 9 gives you a 3. And when you take the product of these two magnitudes, we are, of course, talking about multiplying
6.
2 times 3, which will end up giving us 6. So what this 6 tells us is that when we draw the vector for this product vector, for the 2 times 3, we should basically be getting a length of 6 units. Now, what direction do we plot our vector in?
To the right?
Well, what you have to do, and this is the magnitude for the product vector. You have to take the 2 original, because remember, this is still our product rule. So remember how in product rule, we always end up adding our angles together?
Oh, yeah.
So we would still need to do that. We would need to add our angles together. So in this case, that's of course going to be pi plus 4 and pi plus 4. So by adding the angles together, what do we get?
Pi plus 4 plus 5 plus 4.
Oh, come on. This is the sum of the direction angles. Which of course adds up to common denominator is 4, so that's going to be 2 pi. And what is that simplifying to?
Pi halves.
Yeah, very good. Pi halves, and pi halves is going in which direction?
To the right.
Okay, let's take a look here.
Just going up.
Yeah, because it's the 90-degree direction, right? So that means you are looking at going in the 90-degree direction, of course, starting from the origin. And what was our magnitude for the product vector?
6.
6, yeah, so you will be going 6 units on this imaginary axis. If I can get this to draw for me. Right through here, this is going to be our product vector. Now, if we had to write this down as a standard form, what would we write this as? This product vector.
You would write it as 0,6. Is that right?
Okay. Alrighty, and then as a complex number in standard form?
You would just do 6i.
Very nice, yeah. So it would become 6i. Because of course you don't have a real part to that, right? Since your direction is pi halves. So we know our product, when we multiply the two complex numbers, will come out to be just 6i. Okay, any questions on this example?
No.
You guys are feeling okay about this?
Yeah.
Okay. Okay, so this was number 62, and I think that was the last example that I had for us here. So of course, this brings us to the end of chapter 4. So like I said, all of your homework and quizzes are already available, chapter 3 and 4. Now, you will be taking a combined exam for both chapters 3 and 4. So I'll go ahead and open that up this afternoon, and then you have Sunday till midnight to finish this. And the last thing we have left to talk about is chapter 6. So we'll do that next week, and then use the rest of our time for reviewing and going over any questions you might have about anything from the beginning, okay?
Okay.
Alrighty.
Holy cow.
Yeah, I know. We're pretty much done at this point. We're pretty close to getting done.
Yep.
Any other questions you would like me to answer for you?
Not that I have.
Adrian Medina, what about you?
You said that everything is Sunday at midnight?
Sunday at midnight. Yeah, the 20. Oh, what Sunday? The 26th? Yeah.
Okay.
Okay. All right, guys. If you have no other questions, then that's it for today. Be careful, be safe, and I will see you guys on Tuesday.
Alrighty.
All right, guys. Take care. Be careful.
Bye.
Bye-bye.